Okay, let's get started. I'm sorry I had to cancel classes a couple of times this week. I think whatever it is gone. I owe you a lecture for Wednesday, and I'll record it over the weekend and post it on eCampus. Today I'm going to talk about principal components. That's part of what I want you guys to know for exploratory techniques, clustering, principal components, and then briefly I'll tell you over the weekend, the video I'll post, we'll talk about correspondence analysis. So remember, clustering is grouping together things, whether it's individuals in your data set, the rows, or you can group the columns, the variables. Either way can be enlightening. Principal components, let's come to one of our data sets and talk about it in the context of the data. So I'm going to look at the HERS data again. And I think we're ready to load this in. Okay. So these data, remember, have 2,800 or so individuals. These are women postmenopausal. We have 37 variables, and for each individual we have their treatment, whether it was control or hormone replacement therapy, and several other categorical variables like the race and yes or no, are you non-white, yes or no, do you smoke, do you drink, and so on. And then we also have some numerical variables, age and BMI and so on. In our script, we got rid of any individuals who had missing values, and we got rid of some of these variables that I don't know the definition of, but that have too many missing values for us. So there's weight-height ratio, and then there's weight-height ratio 1. There's glucose, and then there's glucose 1, and so on. And I'm getting rid of all those variables that have a 1 at the end. So I'm going to run this. And now we have 2,738. So we lost 15 individuals. And we have fewer columns because we got rid of some of them. Okay, so we did cluster analysis already. Let me just briefly revisit that. Cluster analysis is applicable to numerical variables. It's all about distances. If we're going to cluster, for example, the people together, we're going to do it on the basis of how close they are to other people. Take all their numerical variables and you can compute vector distances between all the individuals. So clustering works with those. All right, I'm setting aside the numerical variables into a new object called data num. And then we did our clustering. So here's our dendrogram and plot of merge heights. Okay. So we've already talked about this a little bit, and the things you want to think about when you do clustering are how many clusters are there, if there are any, and we think about that in terms of let's say a combination of just visual inspection of the dendrogram together with the picture of the merge heights. The merge heights, we're looking for where do they stop dropping substantially. Once the merge heights are down in kind of the weeds like this, when we're putting things together with those distances, we're going to think of those as indistinguishable from just random associations. The associations, the clumpings that we treat as substantive are those that have big distances that are required to make those joints. When there's a big distance between cluster A and cluster B, that argues for them being real clusters, A and B, as opposed to A and B having a really small distance, like down in what I called the weeds down here, may well just be an artificial association. So asking how many clusters there are, and then once you have decided how many clusters there are, a natural thing to do is to investigate what makes them different. And that's where we did computing cluster averages of the different variables by cluster membership. If we say 5 clusters, for example, we can summarize the averages for each of the variables by cluster. Here's how you can do clustering on the variables instead. All you have to do is when you compute distances, you transpose the data matrix so that you're computing distances between columns instead of distances between rows. Okay, so principal component analysis. Let's see what this is about. I'm going to write down some things on our whiteboard to get started. So let's suppose we have a data set. Let's call it capital X, and it is n by p, a matrix. N rows, that's n individuals. P columns, that's p, we're going to say numeric variables right now. For a data set like this, we can think of this like multivariate data in the sense that for every individual, so let me write this out. We have x11, x12, ... x1p. Those are the p numeric observations for individual 1 in the first row. And then here are the p numeric observations for the second individual all the way down to n. Okay. So each column contains all the observations in our sample on one variable. We can talk about the averages of each of the variables. We could also talk about the variances of each of the variables. So for variable 1, for, let's say, variable j, call it xj. There's a mean, so there's an expected value of xj, and there's a variance of xj. And we could characterize and estimate both of those by just looking at the jth column. Give me all the individuals' measurements on variable j. We could compute a sample average to estimate the expected value. We could compute a sample variance to estimate the variance. So we would have this for all p variables, but because these p variables are measured simultaneously on each of the individuals, it's a multivariate data set in the sense that simultaneous observation of multiple variables, multivariate, not just one number per individual, but p. So not only are there means and variances, there are also covariances, co-relationships between the variables that we have data on. The fact that you measured p variables for every individual means you can also talk about joint relationships between the variables. So we could say there's covariances also. And we can represent all of that, at least the variability information, with a variance-covariance matrix. So here's a p by p matrix. It's a square matrix, same number of rows as columns. It's going to be symmetric. And what it contains, we can say sigma 1, 1 is the variance for variable 1. Sigma 2, 2 is that for variable 2, down through p, p. Those are all the population variances for the variables we're observing. And then what goes in the off diagonals are covariances. There is a covariance between variable 1 and variable 2, ... between variable 1 and variable p. And then here we have sigma p minus 1 with p. And this is symmetric. The covariance between variable 1 and variable 2 is the same thing as the covariance between variable 2 and variable 1. Covariance, just as a reminder, covariance between xj and xk is equal to an expected value. So it's xj minus the mean for xj times xk minus its mean. Definition of covariance. And then the correlation, something we're maybe more familiar with, at least in name, is just a scaled version of the covariance. It equals the covariance divided by the square root of the product of the variances. Let's say j, j, k, k. It takes the covariance, which can be any number on the real line, negative infinity to infinity, and it scales it, and the particular form of this scaling forces the number to become a correlation, which is a number between minus 1 and 1. But it speaks to how they correlate, how they co-vary in a linear way. I mentioned this before. Correlation is a measure of linear association. So imagine drawing a scatter plot of all your xj measurements versus your xk measurements. And if it's a linear looking relationship, then correlation is a single number summary of strength of that relationship. But remember, if your data do not have linear relationships, then correlation is not easy really to apply. It's only talking about linear. Okay, so for our data, bunch of numeric variables, we can represent total variation, all the variation in terms of this capital sigma, a matrix of variances and covariances. Thinking about our variability as information content is where we're heading. Suppose you want to, let's say, distinguish individuals, the women in our LDL data set. Suppose we want to spread the women out with one number in such a way that we spread them out in the most. Spreading out the women, giving each woman a single number instead of 7 or however many numbers we have, p, would require computing a number, a variable, that has big variance. If you want to take your however many people we have in people and summarize them in a low-dimensional way, we have lots of variables. Wouldn't it be nice if we could have a single variable? Give that number to each individual, then you could spread them out and say we have some people who are low in quantity, we have some people who are medium, and some people who are high in the value of this number. It would not be informative, for example, to summarize all the women in our data set with the same number. Every woman gets the number 1. If you plot that, you have everybody at one spot. It does not tell you anything about the nature or the structure of the data. So what we're going to do with principal components is think about how can we take our p variables, p numeric variables, and reformulate them or kind of boil them down to a smaller number of variables. We could start with 1. What if we wanted just one variable that optimally spreads out our individuals in terms of the p variables? Okay, so that's where we're headed. We're going to try to take this variance-covariance matrix, think of it like the total information content in our data set. In an effort to learn about structural relationships, like big picture, what makes this data set the way it is, we're going to try to answer that by boiling the variables down to a smaller collection, reducing the dimensionality to a smaller size. The value in doing that is that you can look at small dimensional stuff a lot more easily than you can high dimensional stuff. So for example, suppose we could construct 2 variables, just 2 variables, instead of the 20, however many we have over here, 28. Suppose we could boil this down to 2 variables, make a plot of those 2 new variables, and reveal, a lot about the nature and the structure of the data. Okay, so here's the short story. With a covariance matrix like this one, it turns out that of all, let's consider creating new variables. Okay, I want to take my p variables and use them to create new variables. There's an infinite number of ways you could do that. We could say x1, the new one, is just some function of the original ones, x2 ... xp. And we could try any number of functional forms. Could be a quadratic, could be a linear, could be a step function. What we're going to do, for historical reasons and because the math works out elegantly, is consider linear combinations. One way to take p variables and boil them into one number is to linearly combine them. What all that means is we're going to find a constant, call it A11, that we multiply by the value of x1, and then plus another constant, call it 1, 2, times x2, plus ... A1p times xp. A very simple way to take p variables and turn them into just one. We're going to consider variables like this, linear combinations of the original variables, and our target is to pick the constants A11, A12 through A1p so that the variance of x1 star is maximized. What is the most informative linear combination of my p variables that we can do? It's a little bit counterintuitive maybe because we think about variance as being maybe a bad thing. You don't want a lot of variance. It makes it harder to see stuff. But for the task that we have here, we're trying to find a way to take high dimension down to lower dimensions in a way that you preserve as much of the real patterns that are there in the high dimensions. Can you take high dimensions down to low dimensions? And capturing and preserving all that variability translates to you need these new variables to be high variance. Otherwise, they're not informative. They don't tell you anything. So pick the constants of a linear combination such that the variance is maximized. And that has a mathematical solution, which is principal components. So the solution. Let's say that A1 is a vector. we have A11, A12, dot, 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 A1P. We have P constants for creating this one new variable. So I'm going to say A1, let's do A1 transpose, is the vector of the constants. A11, A12, A1P. Pick A1 transpose. Pick A1 to be what we'll call E1, where E1 is an eigenvector. E1 is first eigenvector of sigma. So this isn't a linear algebra class. I don't require that you know all the math behind eigenvectors and eigenvalues, but I think it would be good. Go do a little bit of reading on it. The book Introduction to Statistical Learning, Intro to Statistical Learning, has a free PDF online that you could check out. And the last chapter is unsupervised learning, is what it calls. That includes clustering and principal components. So there'd be a little bit more on that there. Yes? How do you order eigenvectors? It's going to be the eigenvector that has the largest eigenvalue. So I'll clarify that. The eigenvector with the largest eigenvalue. So if you take a square symmetric matrix like capital sigma, it's a natural, or it's an easy calculation for a computer at least, to give you back eigenvalues and eigenvectors, and it gives it back to you ordered by the eigenvalues. The first one it shows you is the first eigenvector because it had the biggest eigenvalue. What is eigenvalue? Let me tie that together here. The solution for finding the one variable that is a linear combination of our original ones that will maximize the variance is to take the constants from the first eigenvector. Okay? And what we said the task was to pick A1 such that the variance of x1 star, which we can write now as variance of A1 transpose x. A1 transpose is a 1 by p vector. X needs to be the other way around. Hold on. X is n by p, and A1 is p by 1. So if you matrix multiply n by p by 1, you get row by row the linear combination for that individual. So we're going to have an n by 1 vector, one number per individual. Each one of those numbers is the appropriate linear combination of that person's variables. And it turns out when you pick your linear combination from the eigenvector, the variance of the new variable, x1 star, equals lambda. That's the eigenvalue. So square matrices have these eigenvalues, eigenvectors. Okay, so it's a mathematical notion. It's a little bit hard to give intuition to what it's doing. But in this case, if we want to just summarize a data set and explore, quote, structure, we're going to use eigenvalues and eigenvectors. I don't need you to go get all the mathematical background on it. Trust me, there is a thing called eigenvalue, eigenvector. and it gives us this result that we want. Let me continue with one more step, and then I'll go show you what it looks like. The real value of principal components is seeing it in action and then applying it to your own data. We have just seen if you want one variable from your p variables, and if you're okay with limiting your scope to linear combinations, then we have an answer for the first variable. One variable would be given by x times a1. Okay? So now suppose next step is find a new set of constants for a new linear combination. Find that one so that the variance of x2 star, which is the variance of x times a2, is maximized subject to a constraint. Because we just found a1 that maximizes the variance among all linear combinations. If you were to multiply a1 times 5, say, every number in a1 gets multiplied by 5, then the variance will increase. So you can change, you can increase the variance if we don't make a restriction here. We could increase the variance arbitrarily by just multiplying by constants. The way we guard against that, that wouldn't be extra information. You know, if the nature of the relationship, the first most informative nature is such and such, if all you do is amplify that, you didn't tell me anything new. So what we want for finding our second variable is, again, maximize variance, because variance speaks to information. But to make sure that this new variable tells us something new, we say that we require a1 transpose a2 to be 0. All that means is a1 and a2 have to be perpendicular, orthogonal. That means the story that a1 tells us is uncorrelated with the story that a2 tells us. With these two variables, we'll be therefore able to say, here's the way that our data in one dimension is maximally separated. And here's a perpendicular, uncorrelated, totally different way that you can separate them next best. So in this case, the solution is to make x2 star equal, let's do it this way, to set a2 to be equal to e2, the second eigenvector of sigma. And then we have that the variance of x2 star, same thing as the variance of x e2, is lambda 2. I should have put lambda 1 on the previous slide. This is lambda 1, and that's the first eigenvalue. So the variance of the first new variable, we'll go ahead and give this new variable a name. x1 star is the first principal component. The first variable we created, p variables down to just 1, we call that new variable, the first one, the first principal component. And the variance of that first principal component is lambda 1, the first eigenvalue. Now we have the variance of the second one, which is in a different direction, perpendicular or orthogonal direction to the first one, has variance lambda 2. Second eigenvalue. of sigma. And you could keep going. If you have p variables, there's p eigenvalue eigenvector pairs. Typically, we want to go from p down to much smaller than p, 2 or 3. Okay, let me say a couple more things real quick here. Okay, so we have capital sigma. That was covariance matrix. So we have variances down the diagonal for each of the p variables. And then covariances out here. Okay, so imagine taking the sum of the diagonal. That would be the total of the individual variances. Think of that like the total variability in your data. That's the total variation. And it turns out that the sum from j equal 1 to p of sigma jj is equal to the sum j equal 1 to p eigenvalues. The total variation, think of it, variation as information, so the total information content is equal to the sum of the eigenvalues. What that means is, let's take lambda 1 divided by the sum of the lambdas. This is then the percent of total variation explained or captured, represented by principal component 1. So what we're going to do is take our data, create a covariance matrix, do eigenvalue eigenvector computations using PRComp and R, and then with the output we'll be able to say the first principal component explains 70% of the variance. And the second principal component explains an additional 10% of the variance, say. Once you keep going beyond 1, 2, 3, a handful of principal components, typically the proportion explained goes down to a pretty constant low rate. And okay, and then what we will do is make pictures like this one. Principal component 1 and principal component 2, say we just look at the first two, we can make a scatter plot of these two variables now. You can't look at a scatter plot of 20 variables, but you can of 2. And you'll see the data doing various things, and you might see some obvious grouping or clustering, like this right here. We have what looks like a grouping of individuals there, and then there's a separate grouping over here. And we'll be able to say this horizontal direction, the first principal component, explains a stated level or a stated percent of the total variance. So we might say this is 70% worth of the story, and maybe this is 10% in a different story. And based on a picture like this, the horizontal direction is by far the most informative because it explains a whopping 70%. I'm making that number up. We'll see different numbers for different data sets, but let's suppose we do this analysis and it tells us first principal component explains 70%, second explains 10%. Then interpreting this picture, we would say that the primary direction of interest is the horizontal one, because that explains most. And then the fact that there are some points that horizontally are distinguished from others would tell you there appears to be some real structure in the data. These individuals are different from those individuals in terms of their p variables. And then with less emphasis or less weighting, because the vertical direction explains less variance, you could look at the vertical direction as well. Not a whole lot that's interesting in the vertical direction in the picture I just drew. So we can look at a picture like this, and one more thing, and then we'll see data. So after doing principal component analysis, we can make a scatter plot of first 2 or 3, if you're comfortable with a 3D scatter plot. Make a plot, PCs. What we can also do, let's say that the first principal component explains 70% of all the variation. It seems like a really informative variable. Then we could learn further about the nature of that variable by inspecting its the coefficients that define it. PC1, remember, is x times a vector of constants a1. So there's p numbers in that a1. And if we look at the numbers in a1, it will tell us what the nature of PC1 is. For example, suppose a1, if we had, let's say we have 10 variables, p is 10. What if a1 is just 1 over 10, comma, 1 over 10, comma, dot, 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 1 over 10? If that were what it was, then an a1 essentially is just average the variables, which often happens. The most informative linear combination of all your variables may be like an average, just a straight average. Or it might be a weighted average. Some of the variables might have bigger coefficients than other ones, but they're all positive maybe. So it's still like an average, but you're weighting by different constants. Or there might be contrasts in the code. Suppose the first few variables have big positive coefficients and the next few variables have big negative coefficients. Then that would tell you the way to explain how individuals are different from each other primarily is to take these variables and contrast them with those variables. There are people who are big on these and low on those, and vice versa. And you're going to see that separation when we make a picture. So we can investigate the coefficients of our linear combinations and learn about the nature of what makes things different. The scatter plot tells us about what structure is there, what is different. The investigation of the coefficients tells us about how are they different. Okay, so now let's do this. Back in the R script, hers a LDL, we already have numeric variables. So data underscore num contains all our numeric variables, and we are going to compute principal component analysis. There's multiple ways to do this. I'm asking you in the homework to use PRComp. So let's come over to R and check out PRComp. Question mark PRComp. Performs principal component analysis on a data matrix. So what we need to provide what we're going to provide is just a matrix X. X, the argument X, is a numeric, just a numeric matrix for us or data frame, and it's expecting to have individuals in the rows, variables in the columns. So we should be able to just do prcomp data underscore num. All right, so there's goodies inside PC underscore out. There's a couple of different ways to view the goodies. One is just to say print PC out. Just type PC out, hit enter. It'll show you some information. You can see additional information if you ask for the summary of PC out. Here's PC out, just the default print. And it's got some language that we need to explain. Standard deviations are the standard deviation of each of the principal components. So the square of each of these numbers equals eigenvalues. The square of those equal the variance of the new variable. In the rotation element, we have the coefficients that were used to create the new variables. So for example, PC1, column 1 of the rotation element, has these numbers. Age times 0.0025 minus 0.043 times weight minus that times BMI and so on equals principal component 1. I'll come back to that in a second and we'll interpret that. For now, let's ask, we need to do the summary real quick. So that was the basic print out. If you do summary, it tells you the proportion of variance explained. So it's going to compute for us that thing I wrote on the whiteboard, eigenvalue divided by sum of eigenvalue. The proportion of the variance, total variance, that's explained by this first one. In our case, the first principal component explains almost half of the variance, which is not insubstantial. There's 12 variables for us. Is that right? Dim, data, num. Yeah, 12 variables. So there's 12 principal components that we could compute. Only one of them, just one of them, can explain almost half of the entire story. The second one, if you look in the table of output, we have in the second row here the proportion of variance explained. First principal component explains 46%. Second principal component explains 29%. And then in the third row, it's accumulating these percentages. So third row of column 1 is the same as the second row, 46%. But third row of PC2 is the 46% plus the 29%. So collectively, the first two principal components, take 12 down to 2, you can explain 3/4 of the story. And if you keep going, the third principal component picks up an additional 14, and so on. You can see out in the later principal components that these are very subtle patterns that are being picked up. These are not what I would call like structural patterns. So typically we would look at the first few. It would be nice if the first 2 or 3 could accumulate up to explaining, say, 95%, the vast majority of it. To get up to 95%, we have to go out to 5 dimensions. And I can't draw pictures with 5 dimensions. So I'm going to go ahead and pick the first 2, and I just have to recognize I'm going to see some patterns, but that's not the entire story. It's the bulk of the story. Okay. what happens? I want to compute the principal components now. That's not in any of this output yet. The principal components, like the first principal component, is going to consist of 2,738 numbers. Because every individual, every row, we're going to take their 12 variables and do a linear combination with that set of coefficients. So each person is going to get one number for the first principal component. And I'd like to compute those so we can make the picture that I was showing in the whiteboard. What happens if we do... There's multiple ways to make the picture. I would like to find the simplest one possible. I think this is it right here. Biplot.prcom. Biplot, object of class. All right, let's try this. Biplot.prncomp. Picture of choices equals 1 to 2. Okay. Biplot is jargon for making that scatter plot I was talking about. If you do principal components and you want to visualize in lower dimensions, think biplot. And there's a built-in function for doing this. We're going to say biplot, pass in the object that contains the prcomp output, and choices, as far as I can tell here, is what dimensions do you want? Do you want the top 2 or just the top 1? I don't know what it'll do if you ask for 3 or more. We're going to ask for 2, which is the default. So let's try just doing first 2 principal components, biplot PC out. Over in the help file, just FYI, this function, the help file, is for a function called biplot.prncomp. What that means is it's a special method, or let's see, what's the jargon? I forgot. It's a special method of a general class of functions. There is a general function biplot, and it will do different things depending on the type of variable that you pass to it. There's often this type of thing, like plot is a generic function in R, and it does different things depending on what you ask it to plot. So there would be a plot.ANOVA, a plot.LM, a plot. Lots of other different things. We're looking at a help file for biplot.prncomp. So this is the biplot method that's specific to prncomp. What that means is you don't have to specifically say biplot.prncomp. We're just going to say biplot, and it will figure it out because it knows what x is. It knows it's from prncomp. So biplot PC out. Let's see what we get. Warning message. Let me make it so we only have one plot instead of multi-plots. Okay. So I would like you to be able to make and interpret one of these types of pictures. When I get a data set, I always do clustering, always do principal components. If I have a lot of categorical variables, I'll tend to do correspondence analysis. But I think these are 3 good off-the-shelf exploratory techniques for looking at data. All right, so here's our picture. It's not that interesting of a picture in this case. The first principal component, remember we said, explains almost half. And so we could look at horizontal deviation, horizontal patterns to try to explain it. And there's not any real obvious grouping where like distinctions between some individuals relative to others. So the picture doesn't say much about distinct groupings. If there was a blob in one point and another blob separately, that would tell us about distinctions, which would be interesting because we have a treatment and control group here. If you saw two distinct blobs, possibly that's control and hormone replacement therapy. We don't see any real big distinction among the individuals. Part of what that would tell me is there's not like really major gross differences among the individuals. They're fairly homogeneous, even though we can spread them apart to the tune of 50% variance explained. For the second principal component, only explains a pretty good amount, 29%. There is a little bit of patterning. In particular, there's these points up here that stand out from the bulk, and there's a few points down here that stand out from the bulk of the rest. I'll say more about these red arrows, directed arrows, in a moment. So we've made the picture. Haven't learned all that much yet. We're going to go to the second step of interpreting principal component output, and that is to look at the coefficients here. So let's look at this first column of coefficients. The way you define principal component 1, in this case, is as 0.0025 times variable 1, which is age, minus 0.043 times weight, and so on. We have a bunch of numbers. Some of these numbers are substantially bigger in magnitude than others. For example, the biggest magnitude number is this one, Tg. The coefficient is minus 0.9, as compared to a coefficient for age of 0.0025. Interpreting these coefficients is somewhat subjective, and what people typically do is try to ignore the coefficients that are small and really just focus on the big in magnitude coefficients. So roughly speaking, what we have here, let's say we ignore all the numbers below 0.1. We think they're insubstantial, relatively speaking. What we would say principal component represents, principal component 1, let me write it down, with the HERS LDL data, PC1 is approximately, let's do so approximately, I'm going to say minus 0.12 times glucose, minus 0.33 times total cholesterol, minus 0.22 times LDL, and minus 0.9 times Tg. So I'm essentially ignoring all the low magnitude coefficients and saying, roughly speaking, PC1 is this. All those coefficients are the same sign. Sign is actually not really an issue when we do principal components. You could multiply all these numbers by minus 1 and still be representing the same pattern. You would have to multiply all of them by minus 1. You don't get to arbitrarily pick a few of them to change sign, but if you change all the signs, it doesn't affect the interpretation. So we might as well just say plus for each of these numbers, in which case this is a weighted average. We're giving 0.12 weight to glucose, 0.33 to total cholesterol, 0.22 LDL, and a whopping 0.9 to Tg. So you might say this is largely the Tg variable, combined with, in a lower significance, these other three. Sometimes when you write this down, there's a pretty nice interpretation that falls out. Oh yeah, it makes sense. You would be able to see differences in these people based on the difference between BMI and total cholesterol or something. I would take this relationship, this result, to the PI and say, here's what we're seeing. In your data, the biggest source of pattern and structure is apparently this. Does that make sense? What it's probably saying in this case, often when you do principal components and the coefficients come out, or at least the meaningful ones come out as all the same sign, you can think of it like an index kind of thing. If you look at the Introduction to Statistical Learning book in Chapter 10, they talk, for example, about a stock market example. They take some stock market price data, they do principal components, they make one of those scatter plots, they look at the coefficients, and the first principal component is a weighted average of all the stocks. Like 0.3 times stock 1 plus 0.4 times stock 2 plus ... a bunch of positive coefficients. And they characterize that as an index of the stock market over time. You get that when the primary source of structure is just that you have some people who are, or you have some stocks that went down, some that didn't do so well, and some that went up on a continuous scale. Not a distinct separation, but on a continuous scale. Same kind of thing is happening here, apparently. The women can be separated in terms of these four biomarkers, and there's a continuous separation. Some women have low glucose. They tend to also have low total cholesterol, low LDL, and low TG. Other women have the opposite. And everywhere in between, there's a continuous spectrum. That's principal component 1. Now let's look at principal component 2. PC2 explains 30-something%. What time does our class end? 1:30? Damn, sorry. I'll pick it up next time. But real quickly, you can see PC2 largely is, here's two big positive numbers, and here's one big negative number. All the other ones are insubstantial, arguably, compared to those. So roughly speaking, PC2 is an average of total cholesterol and LDL contrasted with TG. Okay, I will let you go, sorry. Another video coming this weekend over correspondence analysis. I pushed the homework due date back to Wednesday, so you have more time, and you have another Q&A with me in particular on Tuesday night. You are all welcome to come to the Q&As. We did have a few people there this week. They are recorded, so you can always watch them on your own time. If you can't come, you're always welcome to send me questions through the discussion board. Could you please talk about such and such, and I'll do that in the Q&As. Okay, thank you. Have a good weekend.